Okay, well, we'll see how this focus is. For those of you who aren't here, it's Thursday, November 1st. It's either one day after or anywhere between 4 days prior to Halloween in the state of New Jersey, depending on where you're at. So, and if you're not here and you're not here because of the storm, we're thinking about you. We'll see you next week. Take care of yourselves. Questions? Oh, you had a week and a half to prepare for that statement. Come on.
Whose keys are these? Oh, that's mine.
Well, I did ask questions. I wasn't specific, so. It's a lot more fun having people in front of me. By the way, did you like the Who's Line thing?
That was cute. I laughed. My mom was like, what are you laughing at? I thought you were watching a math video. And I was like, I don't watch this.
Yeah, one of my other classes, while I'm giving you a moment to look, at one point in the video, I all of a sudden said, now I'm sure that everybody in the room can handle the algebra, and then I paused for a second, and I went, wait a second, I'm the only one in the room. Well, I'm still sure that everybody in the room can handle the algebra. Anybody find anything? Yes.
In 3.7,
Yeah.
number 105.
Okay. In case you didn't hear that, section 3.7, number 105. What page is that?
129.
129. Okay. So, this says, in Southern California, a growing number of individuals pursuing teaching credentials are choosing paid internships over traditional student teaching programs. A group of 8 candidates for 3 local teaching positions consisted of 5 who had enrolled in paid internships and 3 who had enrolled in traditional student teaching programs. All 8 candidates appear to be equally qualified, so 3 are randomly selected to fill the open position. Let Y be the number of internship-trained candidates who were hired. Okay, so can you tell, are we going in and out of focus? We're good?
It doesn't look like it.
Okay, thanks. It's either that or what you ate for lunch. So, okay. Does Y have a binomial or a hypergeometric distribution? Y, okay. Just remember, the answer to the question Y is not because it's in the hypergeometric section. Okay, so it is a hypergeometric, but why is it a hypergeometric as opposed to a binomial? It's been a while. If you go back, what were the properties of the binomial? What were the different properties it had to hold? Okay, so two outcomes or 2 events. We've got that, right? Because they're either paid internship programs or they're student teaching programs. So that part matches up. Okay. What else did we have in the binomial? Yeah.
Equally likely. No, that's wrong.
Okay. Yeah, you're thinking of the right thing, but what's equally likely?
That either event will occur? No.
No, that's not what's equally likely, because that would mean we'd have to have a 50-50 situation each time. So something is equally likely, but it's not that a success is equally likely to a failure. It's that a success is equally likely on every single trial, right? Constant probability of success, okay? Remember, the other 2 are, we have a fixed number of trials. Okay, do we have a fixed number of trials here in this problem? Go to the next to the last sentence in the question. Yes. Okay, what is that fixed number of trials? Hmm? Three, right? Because we're selecting 3. Okay. Do we have a constant probability of picking an internship trained candidate? No, right? Because we're sampling how? Okay, we're doing it at random without replacement, and we've got a small group, right? So we start out with 8, and then whatever we pick the first one, it goes down to 7. So for the next trial, we're looking at the number of internship candidates, and there were 5 in those internships. So on the first one, it's 5 out of 8 chance of picking an internship candidate. On the second one, it's either 5 out of 7 or 4 out of 7, both of which are dramatically different from 5 out of 8, right? So with the hypergeometric, remember that you're working with smaller population sizes, smaller, could end up being smaller sample sizes. It doesn't have to be. The number of trials can be small in either case. But in the binomial, if we're doing a finite population, which we talked about in the video, it would have to be very large relative to the sample size, and that's certainly not the case here. Okay? So, as far as this is concerned, why is the number of internship trained candidates? We said that little n is equal to 3, cap n is equal to what's the population size in this one? 8. And R is remember what R stands for? Yeah, it looks like you were about to say.
I changed my mind, I don't want to say it. I'm afraid I'm wrong.
I'm not going to mock you, you know that.
I just told him to say it.
Yes.
5?
5.
That's what I was gonna say.
Sure
I was
you
holding
were.
my fingers up. I was really busy.
Just think about it. Some point tomorrow, I was probably too close to the microphone. They had their volume up and they just blew their ears out. Okay, R is 5, right? Because remember, that's the number of people in the group that we're counting. That's the internship trained candidates. So if we look at P of Y, what we've got here is 5 choose Y. What goes in each of those 2 spots? Not 8 minus Y, 8 minus R, right? So remember, the numerator we're dividing up into our 2 groups. So we've got the internship trained and the student teacher. Now, down here is where we need Y, a function of Y. What's going to go there?
Capital N minus Y.
Close. Little n minus Y. So 3. Not the 3 that's up here. It's that 3. Okay? And then in the denominator, it's going to be what choose what? A choose 3, right. Okay. So for part B, where it says find the probability that 2 or more internship trained candidates are hired, since we're only taking a sample size of 3, for part B, you need to do P of 2 plus P of 3. And I trust you can plug that in at this point. So, for C, the mean and the standard deviation, go to the formulas that I gave you that are also in the book, plug in the corresponding values and get your numbers out. Okay? Okay. Anything else?
Section 3.3, number 31, part B.
2, 3. Wait a second. 3, problem 31.
31, yeah.
Part B? B or D? I'm sorry.
B.
B. Okay.
B.
That wasn't part of the homework.
Oh, I looked at it wrong. Okay.
Okay.
And with that, all right.
It should just be 2. It should just be 2 mu, 2 times the expected value of y. But yeah. Anything else? How's the focus now that they're writing on the board?
Looks good.
Looks good. Annie?
38, 125.
Okay, page 136. Okay, so this is going back to 120. How was 122? Fine? Okay. So,
I just couldn't find T.
you couldn't find in 125?
Yeah.
Page 136, problem 125, right? Okay. So just going back to 122, it said, customers arrive at a checkout counter in a department store according to a Poisson distribution at an average of 7 per hour. So we've got, from 122, we have lambda equals 7 per hour. In 125, if it takes approximately 10 minutes to serve each customer, find the mean and the variance of the total service time for customers arriving during a 1-hour period. So, and we're looking for the mean and the variance of the total service time. Okay. So if it takes 10 minutes to serve a customer, then the total service time should be the number of customers who show up times 10. Okay, so okay. So, but the number of customers who show up is a random variable, right? So, if X is the number of customers who show up in an hour for a Poisson, what's the value of the mean? Hmm?
7.
Okay, 7. So in general,
Oh, yeah, it just equals the mean.
it equals lambda, right? Right? Okay. So and variance of X is also lambda, right?
But in the back of the book, it says 700. That's where I got
Oh, do
confused.
you multiply that?
Okay. For the variance?
Yeah.
Okay. So we're looking at the expected value of 10x and the variance of 10x, right?
Oh, okay.
So you got 70 for the first one, right? What happens when you pull the multiplicative constant outside the variance?
It's squared.
It's squared. And that's where your 700 comes from.
Is this the other one's 7?
Huh?
One's
So-
7 and one's 700. It's not 70.
Well, it should be 70.
Okay.
It should be 70. 70 and 700. Okay? Any other thing else? No? Okay. So. Now, the section that we've got for the remaining time that we have today appears in both chapters 3 and 4. So section 3.9, and I think it's also 4.9, but there's some, no, it's not. Is it 4? No, it is 4.9. Okay, 3.9. And also 4.9 has to do with what's called the moment generating function. Abbreviated MGF. Just as with the stuff that we did in 3.2, 3.3, 4.2, and 4.3, we had discrete versions and continuous versions. Moment generating functions exist for all types of random variables. Okay. So the stuff that we're learning in 3.9 carries over to 4.9. The only difference between them, again, is that we go from summations to integration. Okay. But all of the concepts are exactly the same. So here's what I'd like you to do to start this. And you've got the following function here. I'm going to call this m sub x of t. And this is going to be e to the negative 2t plus, this should be 0.2 e to the negative 2t plus 0.5 e to the 7t plus 0.3 e to the 10t. So the first thing that I'd like you to do is to get the first and the second derivatives of this function with respect to t. So, big questions. How well do you remember how to differentiate exponential functions without turning on a calculator?
That's what it's for, isn't it?
Remember I said there are certain basics. Anybody in here who's, and I know there are people I've talked to about the whole actuarial thing, anybody who's interested in doing that isn't going to be allowed one of those in the room, so. I don't remember what they let you have for a praxis.
They let you have
The 89 or the 84?
89.
Really?
Yeah.
Wow.
They don't let you have scrap paper though.
Really?
It's retarded. It's very backwards.
Okay. If you know the first one, the second one should be pretty straightforward. So for the first term, what's the derivative?
-0.4 e to the negative 2t.
Yes, negative 0.4 e to the negative 2t. Chain rule, right?
Yes.
Derivative of e to the at with respect to t is a e to the at. So we got negative 0.4 e to the negative 2t for the next term. Coefficient's going to be 3.5 e to the 7t, and then 3 e to the 10t. Okay. So for the second derivative, we've got 0.8 e to the negative 2t plus 24.5 e to the 7t plus 30 e to the 10t. So, what do you get in each case if you evaluate this at t equals 0? Basically, what's going to happen in each one of those terms when you let t equal 0? What's going to be 1? The exponential part, right? E's not going to be 1. E to the whatever power is going to be 1. So basically, all you're getting is the sum of the coefficients. Okay. So in the first case, the sum of the coefficients, we've got negative 0.4 plus 6.5. So this is 6.1. And in the second case, 54.5 plus 0.8 is going to be 55.3. Okay? Okay, so now I got a probability mass function. The values in my mass function of x are negative 2, 7, and 10. The probabilities are 0.2, 0.5, and 0.3. So what I'd like you to get now are the expected value of x and the variance of x for those. And instead of you sitting at home with the camera on watching them work and me do nothing, I'll pause it.